Hello, my name is Puanon from class 612, number 22.
Hello, my name is Sitapat Hongwansit, number 16. Hello, my name is Chayapol Novintrankulai Chaya, number 14. So welcome to our presentation, and in this video we will be presenting about the photoelectric. And we will be explaining about what is the photoelectric effect and what the classical physics predicted about it. Third is what is the actual experiment results revealed to us, and fourth is how these results supports the photon model of light, and lastly is a comparison of the results of different metals and Leibniz graph. So we will be also dive into key concepts like quantity, energy quantizations, threshold frequency, and the difference between how intensity is understood in classical and quantum physics. We will be using a simulation to bring this idea to be more clearer and as a source of presentations. So first off, on the photoelectric experiment, the photoelectric effect happens when the light strikes on the surface of a metal and cause electron to be ejected. And here's how the experiment is set up. First off, we need a light source that emits of a specific frequency and intensity onto a metal surface, and if the conditions are right, the electron will be ejected from the metal. This eject electron will create a current, and which can be measuring using a detector. So there also are several factors that may affect the outcome of the experiment, including the frequency and intensity of the light and the type of the metal being used, because of each metal will have the unique property called the work function. So let's use the simulations to observe the basic setup and how the lights interact with the metal. So first off, the light will flash onto the metal surface. In this case is sodium, and the electron will bounce off and as a kinetic energy, as you can see in the simulations. Now let's talk about what classical physics predict about this experiment. In the classical wave theory of light, it was thought that, first, light is a continuous wave, so its energy should increase with intensity regardless of frequency. Second, as light gets more intense, it should transfer more energy to the metal, ejecting electrons with higher kinetic energy. And lastly, any frequency of light should eject electrons if the intensity is high enough. To put it simply, classical physics predicted no threshold frequency. Electrons should be ejected as long as the light is bright enough. But this isn't what experiments showed. Let's move on to the observation.
So here's what the experiments revealed, which contradicted classical predictions. First, electrons are ejected only if the light frequency is above a specific threshold, no matter how intense the light is. Second, increasing the light's intensity increases the number of electrons ejected, but not their kinetic energy. And third, the kinetic energy of ejected electrons depends on frequency of light, not its intensity. So now let's use the simulation to see this in action. First, we'll set the frequency below the threshold. So bit here. You can see like there's no electrons ejected even if we increase the intensity. So maybe 100. Yeah, there's no electron ejected out of it. Now let's increase the frequency above the threshold. Like this. Now you can see that the electrons are ejected and increasing intensity increases the current. Now see, the current is like 0.019 now. So if we lowered, yeah, it's kind of like lowered to 0.016 or something like that. Yeah.
So next is the photon model and the quantizations. So in these experimental results can't be explained by classical physics, but they can make sense on the photon model of light, which in this model, the light is made up of particles called photons. And each photon has an energy given by E equal to hf, where h is a Planck's constant and f is the frequency of light. And here's how it's worked. So as you can see in the experiment, when a photon hits the metal, the energy is used to overcome the work function, which is the minimum energy that needed to eject an electron. If the photon's energy exceeds the work function and the extra energy becomes kinetic energy of the eject electron, this explains the threshold frequency below it. Photons don't have enough energy to eject electron. So let's look at a graph of kinetic energy and frequency. Notice how the kinetic energy increase linearly with the frequency above the threshold matching the photon model.
Different metals have different work function, so their threshold frequencies vary. For example, metals like sodium have lower work functions, meaning that they require lower frequency light to eject electrons, while metals like zinc need higher frequencies. Let's do the simulation to compare sodium and zinc. First, we will set the light to a frequency above sodium's threshold, but below zinc. You'll see that electrons are ejected from sodium but not zinc. Now we will increase the frequency to meet zinc's threshold, and both metals eject electrons.
And another important graph to look at is intensity versus photoelectric current graph. So you see in the photon model, increasing intensity means increasing in the number of photons hitting the metal, which increases the number of electrons ejected and the current. You can see it in this graph. As the intensity goes up, the graph goes up too, so it's correlated. And this is different from the classical model where intensity was thought to increase the energy of the ejected electrons. Yeah, so here's the graph basically. So now I'm gonna talk about the difference between classical and photon model. To summarize, here's how the classical and the photon model differs. The classical physics says intensity determines energy transfer with no threshold frequency. And the photon model says frequencies determines energy transfer and intensity affects the number of photons and not their energy. And as the experimental results clearly matched to the saying of the photon model, showing that light's energy is quantized and tied to its frequency. This breakthrough led to the development of quantum mechanics and deepened our understanding of light as both wave and a particle. And that was the difference between the classical and the photon model.
So lastly, for the conclusions, the photoelectric effect is a powerful example of how experiment can challenge, establish theories and lead to revolutionary ideas. By confirming the photon model of light, It's paved the way for the modern quantum physics and has the practical application in technologies like solar panels and light sensors.
Thank you for joining us in exploring the photoelectric effect. We hope this presentation clarified how light behaves in surprising and fascinating ways.
Feel free to explore the simulation yourself to see the principles in action. Thank you for listening to our presentation.